Okay, sorry, there seems to have been some screw up with booking. I got an email saying I had that room, but anyway, I'm not going to fight with that. So hopefully I'll get it sorted out and we can have another computer lab in like 3 weeks or something like that. So today I wanted to show you a kind of little bit about Excel. And what we do with Excel is not going to be on any test. You might get homework assignments where you have to use Excel. And for the project that's due at the end of the semester that you're going to present in the last week, it'll be useful for you to use Excel. Now, the reason why it'd be nice to use Excel, it's a spreadsheet, and spreadsheet programs are really good because you can, have a whole thing set up with entries, and what's in one entry depends what's in other entries. So there can be a lot of computation done, and the computer does it for you, which is nice. And also there's various sort of graphical tools at your disposal then. So you can do computations, find results, and you can also, get graphs, pie charts, whatever. So it's really useful. Okay, so is it hard to read? It's kind of hard to read, isn't it? Let me let's zoom a bit. That looks better to me. Okay. So what I wanted to talk about today in this lab, I just kind of wanted to take a little break because we've got the test tomorrow, and I just want to sort of concentrate on this concept that we've learned in the last 2 sections, and that is the concept of finding the derivative. So remember, we've defined the derivative as the instantaneous rate of change of a function at a point. And you can sort of think about, what do you actually mean by instantaneous rate of change? And so for us, what we mean by instantaneous rate of change is the average rate of change we see when we take a really small interval. Okay. Now, that was kind of fudging things a little bit, because what do I mean by small? And the other thing is, how do we know that our answer is any good? Okay, and so that's what I wanted to concentrate about before, because what we're actually doing is doing something called taking a limit. So as a instantaneous rate of change is the limit of the average rates of change as the interval gets smaller and smaller and smaller. Okay, and so remember what I suggested you do? I suggested you take a small interval, and then to double check, you take an even smaller interval to see that your answer is good. That is what I mean by successive approximation. So you don't do it just once. Really, in taking a limit, you should take it more than once, and you should check that you're getting good answers. That gives you another question, right? What do I mean by a good answer? And this is the answer: stabilize. You see an answer that stabilizes. Okay, so the idea is, here is the idea. You want to find something, and you don't have an exact formula for it, but you know you can get it as a limit. So that means you've got a way of approximating the answer. Okay? So once you have a way of approximating the answer, by doing more work, you can get a better approximation. In our case, doing more work means taking a smaller subinterval. And when you take these, that means you've got a successive approximations to your quantity. So you've got kind of like a sequence of things, and you know you've got a good answer if the answer stabilizes. It's kind of like, you know, like when they're solving to crack open the safe. You see this in movies where they first get the first digit, then the second, third, fourth, fifth, sixth, and eventually they get all the digits and the safe opens. Well, that's the same thing with you. You do successive approximations, and each time you do it, you get more digits of the answer until finally you get enough digits that you're happy with. Okay, so I promised you, we talked a little bit about how things can go wrong. So that was the first thing I wanted to show you. So I wanted you to do this for you to do this yourself, but we're going to have to
Is there going to be homework for today or tomorrow?
There's going to be no homework from tomorrow because tomorrow's going to be the test. I might give a homework, like a question or two from this. Yes, so yes. Okay. So this is something that I showed you kind of before. This is this microscope. And it's a tool that we can use, and it's on Blackboard, so you can use it yourself to find out the rate of change. Okay, and so here, this column here gives the x's. Here, the column gives the y's. And if you click on a cell, you see that the function talked about is f of x equals x to the fourth minus 8x. Okay. It's centered at 2, and the average rate of change here is 32, right? Because it rises 64 over a run of 4. Does that sound right? Oh no, 64 over a run of 2. Sorry, that's why the slope is 32. Okay, so that's the idea. So that's our first approximation, 32. So maybe we could write something like this: delta x, and then this is the answer, f prime of 2. So when delta x is 2, over a run of 2, we get a slope of 32. And so then I would say do 0.2, and I see the answer is 24.08. And we've got no stabilization. So we don't really know kind of how our thing is going. So then I do 0.02. And all of a sudden, things are looking good. How many? 08. So now you see the stabilization. So we see that here, that has stabilized. So we're going to be pretty confident that the answer is 24 point something. Okay. So it hasn't quite stabilized anywhere else, right? So this is like 24.1. This is 24.0 going to the next decimal place. So let's do another one. And now it's 24.000. How many? Four zeros and a 1. Okay, and so now we see that it's stabilized to that, right? Because this is 24.001, 24.000. Okay, so we're pretty. So f prime of 2 is 24.00. And we're quite comfortable with that. Okay, so this is what we talked about before, and this is all comfortable with everyone. So this is this idea of successive approximation and stabilization. So this is taking a limit. Okay. Now, the reason why it all works, as I said before, is because what happens when we take a really small window for a nicely behaved function, for a really small window, the function looks like a straight line. And so we know that a straight line, or what straight line is it? This is the tangent line to the function here. So this is really what the derivative is, right? It's the slope of the tangent line at that point. Okay. So what's an example of something going wrong? Oops. Let's. It's so slow. Okay. So, okay, so let's do a new function. So let's go back to delta x of 2. Let's go to 0. So I'm centering my function at 2. I'm centering my function at 0, and my window is 2. So that means I'm going from -1 to 1. And I'm going to change my function. I'm going to have it equal ABS of A1. Oops. Okay, so the function ABS stands for absolute. So now our function is f of x equals the absolute value of x. Has everyone seen this function before? Okay. Now, the way that Excel works is you can put in formulas, and if you want to refer to another cell, you've got to give it the address. So A1 is whatever number is in this A column and the one, oh no, sorry, it should be A2. A1 is not a number. A2 is going to be this number right here. And what's the absolute value of -1? 1. Let me check that. Yes, it does. Now, here's one of the nice things you can do with Excel. So if I highlight the cell and I go to the lower right column like this, and I drag it down like this, I've copied and pasted, and it does what's called dynamic addressing. So here is absolute of A3, A4, A5. So when you drag down, it automatically updates what the address is going to be. So this is just a shortcut way of being able to copy and paste things. Okay, and so here is our function, absolute value of x at 0. And has everyone seen this before? This is what you expected. Okay, so let's do the same thing as before. Let's do f prime of 0. So at 2, the slope is 0. I do 0.2, and the answer is practically 0. What is it? It's like 10 to the minus 16. So let's just say 0. That's actually just a machine error. .02, it's 0. And if I do it again, I'll get 0 again. So you might say, aha, successive approximation, the slope must be 0. But the answer is not 0. Can anyone tell me why? Why have I been leading you up the garden path? Do you see the tangent line there? Yes. So all I'm doing is doing the slope of this line here. You're not seeing any tangent line here. This line here does not have a tangent at 0 because it has a corner at 0. So that's why I put the picture in there. So not only do you have to see stabilization, but you've got to see a straight line. That's just an extra requirement that we need for this thing, just because this thing is not making any sense because we're not seeing any tangent line. Because what would happen if I used, instead of doing interval from minus a to a, what happens if I would do the interval from 0 to, this is using 0 as center point of interval. The derivative I get by using 0 as left point of interval. Right. What is the slope of this, the function that we see in this interval here? 1. I would get 1, 1, 1, 1. And if I was to look at using 0 as right point, I would be getting this. And what's the slope there? -1. So here it stabilizes to 0. Here it stabilizes to 1. Here it stabilizes to -1. I'm not making any sense. You can't have more than one thing being the number, the answer. So the real answer is does anyone know what DNE stands for? Does not exist. Yeah. So anyway. Stop sharing.
But on that one, if they ask you to do the tangent line of like any other, I mean, I guess it would just be the slope at that point, but any point other than the corner, it would be the
Yes.
see the slope.
Yes. So for that function, only at 0 does not exist. F prime of 1 is 1. Because it doesn't matter whether you use 1 as the center point, the left point, or the right point, you would still get the answer 1. And you would get that F prime of -1 would be -1. In fact, F prime of A for any A positive would be 1, and for any A negative would be -1. Exactly right. Okay. So let's okay. Here's another situation. Okay. And this is just, again, another way of just another example of looking at this idea of a limit. Okay. So let's think about finding the length of a curve. Now, finding the length of a curve is another sort of situation where we very rarely have exact formulas. We know what the length of a straight line is. Does anyone remember the formula for the straight line? Sorry?
Y equals mx plus b.
So that's the formula for a straight line, the formula for the length of a segment.
Y2.
So we use Pythagoras, right? Because we can turn this into a little right triangle. And the length of the hypotenuse squared is equal to the sum of these squares. So the length equals square root. Well, what is the length of this? It's A minus C. And the length of this is B minus D. So we square those. So these are the lengths of the legs. We square them and add them. It's going to give us the length of the hypotenuse squared. So to get the length of the hypotenuse, we take the square root. So this is a formula that we can use to figure out the length of a straight line. Okay, so this is something that we've done a long time ago. Now, a famous result from ancient classical Greece was Archimedes wanted to figure out what was the circumference of a circle. Okay. And he had a very clever idea. So what he did was, well, first he put in like a hexagon, and he put a hexagon inside and a hexagon outside, right? And so the length of the circle, circumference of the circle, is bigger than the inside hexagon and less than the outside hexagon. So let me see if I can do that. That should be tangent line to it. Something like that. Okay, so that gives you an approximation to the circumference of the circle. So what did he do next? Sorry? No, because this is nothing to do with tangent lines. It's trying to figure out this length. So what would be a better approximation? So if you then sort of turn the hexagon into a what do you call a 12-sided figure? A duodecagon. And he did that by doing this. After a while, my circle gets very complicated. And he did the same thing with the inside one as well. My drawing is not so good. But anyway, so the inside, let's just call it a 12-gon. And so that gave him a better answer. And so what did he do next? He did a 24-gon. And then he did a 48-gon. And then finally he did a 96-gon. And he came up with his famous this is how he came up with his famous approximation 22/7. He actually got a much better approximation than that, but that's where the thing there. A Chinese mathematician then in the 12th century, which was, do you know what dynasty was ruling China in the 12th century? Song? Yeah. Okay, someone in the Song dynasty. I think his name was Ji Chong. Oh, you know him? Yeah. Okay. He did even more. I forget how many. He did like thousands and thousands of sides, and he got a super accurate approximation from pi this way. So this is how you actually that's actually how the ancients figured out these things like this. Okay, so let's try something similar. We're not going to use geometry. We're going to use just the Pythagorean theorem. And so I constructed this Excel file to help us with that. So again, I've set up a grid of points, right? So I go from 0 to 1. And here is my y, is my function. And we see that we're dealing with the function x squared. So what we've got here, going from 0, 0 to 1, 1. Terrible parabola. But that is the function x squared. And so what we're going to do is we're going to use what we've seen. We're going to use their inspiration to come up with an approximation for the length of this parabola, because there's no formula for that. So what we're going to do is we're going to take a grid of points along this. We're going to take 20 in all. And we're going to use the Pythagorean theorem to figure out the length of that little line segment, and then we're going to add them up, and that's going to be an approximation to the length of the parabola. Do you understand that? Okay, so I'm going to use n is 20, and I'm going to come up with the length. Let me show you how I did this. Okay, so here is x squared. Now here is the length. You see there, you should see, hang on, let's see if I can, how do I make it bigger? I forget how I do that. Anyway, up here, you can just see the Pythagorean formula. So this is a nice thing about Excel. You can just put in whatever formula you want, and the machine will compute it for you. So this is the length of this segment. This is the length of the next segment, etc. So this is the length of all the 20 segments. And then in the total, I'm just adding them up as we go along until finally we get to the last one, and that's the sum of all 20 segments. And so I'm going to write down that, let's say I want to figure this out to 5 decimal places, or let's say 6, because that's what we've got. That's my approximation. And I'm pretty sure it's a pretty good approximation. How do I get a better approximation? Make the interval smaller. So instead of 0.05, let's make it, instead of 1 on 20th, let's make it 1 on 200. When I do that, unfortunately, I only get up to 0.1 instead of 1. So I have to make my file bigger. So what I do is I click here. I keep my finger down on the left button. And so now I've just copied that row. And then I put my mouse over the lower right corner until I see that plus sign. And then I press again the left button and down I go. This, oh, yeah, more than enough. Gone way past it. Let's go back to one. There we go. And so when the answer is, when I use 200 intervals, my answer is 1.478941. So do I see stabilization? Right, because here it's sort of like to the first 3 decimal places, I've got accuracy. This answer is going to be more accurate than this one, but I see that it's definitely going to be something like 1.4789. I mean, I'm pretty happy with this, right? And so maybe I'll do just one more. Just got to be willing to put in the work. Okay, I put in an extra 0. What did I do wrong? Oh. I put an O in and not a 0. Okay. And then I have to do the same thing as before. I have to go down and I have to make it bigger. Oops, one more. Oh, there we go. So when I use 2000, I get the answer 1.478943. I'm really happy now, right? I've gotten a good answer. And so that's just using the process of taking a limit, taking successive approximations. As I said, this is not going to appear on a test because it just takes a lot of computation to do. But the main thing to do is to understand this idea of successive approximation, you know, taking a limit. We're not really going too much in the technicalities of taking limits. So what you're going to do in a test would be, you know, I would give you a function and ask for the slope. You would do a small limit, and then maybe you double check your answer, make sure you've got a good answer. So you would do, like, for example, x squared, or x cubed, let's say. You do x equals 1, you might do this. And then you might do this. And check the answers you get. So if you start off with something which is really good, chances are that your answer is going to be good. And this double checking is just making sure. Okay. Let's just do one more, because this is one of my favorites actually. This is even older than Archimedes. This goes back to ancient Babylon. So this is like 4,000 years ago. Or so, 4,000 years ago. And this is how the Babylonians did square roots. It's actually kind of interesting. I find it interesting. Let's say you had to find the square root of 2 and you didn't have a calculator. What would you do? Well, you'd make a guess, right? So give me a rough guess of what the square root of 2 is around. So let's say 1.2. Okay. Now, another guess, which is just as good, is 2 divided by 1.2. It's just as good a guess as this, because when we multiply these two things together, what do we get? 2. So however much this misses out by being the square root of 2, this also misses out. Now, if one is an underestimate, the other is going to be an overestimate. Right? And so the Babylonians thought, let's just average the 2. And that's going to give me a better answer. This is what the Babylonian scribes did. You know, they did this on tablets of clay. Crazy. Okay? So this is an approximation, a better approximation. So and then you can go do that again. So let's do this. So let's, for example, let's start off with is it Max? No, is it, hello? What's your name?
Oh, Joe. Joe.
Joe. You're Joe. Let's start off with 1.2. Okay. So 1.2, if we square it, we get 1.44. So actually it wasn't that good. But when we take the average of them, we get of 1.2 and 2 divided by 1.2, we get 1.4333, whose square is 2.05. So we went from a crappy guess to a good guess. And so we use that again, we get this 1.414, and its square is 2.000361. So we went from a good guess to a better guess. And then the next one, its square is actually 2. Okay, so in 3 goes, we went from something crappy to something which was fantastic. That's pretty good.
So like it doesn't really matter what your estimate is, then?
As long as it's got to be kind of, yeah, it can't be too goofy, but as long as it's roughly there, it'll get there. And so this again is this idea of successive approximation. Each time you take an average like this, you better get a better estimate. You get successive approximation. And in the end, you get an answer, a good answer, a really good answer. And you see the stabilization right here. Okay, so that'll do us for today. So sorry that the computer didn't work out. You could have done all this by yourself instead of having me explain it to you. Any questions about tomorrow?
What's the structure of the test going to be like?
It's going to be like homework questions.
So is it like multiple choice or is it?
No. It's going to be, you know, like, here's some points. What's the straight line? Which one of these things is concave?
Okay.
That kind of like the homework quiz. There's no multiple choice on the homework, was there?
No, I was
No.
just wondering what the test was.
Yeah. No, it's just going to be like questions like as per homework.
Okay.
In fact, that's where I get I don't get them from homework questions, but I get them from the book.
It's gonna be part of the review stuff we did and part of the stuff we did.
Exactly. It's going to be comprehensive of the stuff that we did. So I know, so we haven't done exams in a while, so you're probably a bit nervous, but I don't know what to say. I don't know what encouraging words to say, but it's going to be okay. I know I curved the test, and we just have to do it and kind of see where you are, and then see if you need to work maybe more on the review or not. Proof's in the pudding, or the eating, or whatever they say.
How do you curve it? Like, do you curve just based on the highest person's score?